Okay, make sure you have your clicker and let's take a quick attendance. We could have quizzes every day. It's possible that we won't on a certain day. Today does not turn out to be one of those days. Yeah, it's okay, as long as it's not grayed out like that. Everybody clicked in? Melina? Okay, here we go. Wait a minute. Who are these people? Does everybody see their name up there? Does everyone see your name? Then who clicked in with these? Anybody that your name's not up there? That's weird. Okay. I'm not sure what that's all about. All right, so let's, we've got a lot to do today. We're going to get into 3.1. 3.1 is going to take us all of today and part of next class. You have the Cipher project that's due today. So here's the way this is going to go. I would like for you to get it and kind of put it on your desk, and you're going to turn it in with your quiz that I'm going to give you, all right? But if you broke the code, I want you to write, because you're only turning in your answer sheet, all right? Your answer sheet is the one that has all your work. If you broke the code, I want you to write the broken code across the top. Now, the broken code will only count as bonus, all right? So if you didn't break the code, it's okay. But the amount of bonus is inversely proportional to the number of students who turn it in. So if you broke the code, don't tell the person next to you what it was, because then the value of the bonus comes down. So if everybody turns in the code broken, it's going to be worth very little. If there's 3 people who broke the code, it's going to be worth more. Does that make sense? Yes? So if you broke the code on your answer sheet, right across the top, and flip it over and leave it on your desk. Everything else off your desk. We will, yes. Everybody good? Everybody ready? Okay, today's quiz is a group quiz. Okay? You can work with one other person. All right, unless you're in an odd group, let me see. Let's see if someone joins. If somebody joins, then y'all need to split into 2. Okay, hold on. If you could please keep your voices down when you're talking to each other. You know, work as a team, but don't be like, oh yeah, you just do that, you know. I want to see what the 2 of you together can come up with. All right? Y'all ready? Now, it is timed, all right? This is a timed quiz, so do not turn this over yet. Do not turn it over yet. I hope not. All right, hold on. Let me figure out how much time I'm going to give you. Okay, just keep it there. We're going to go 7 minutes and go. Make sure you write your name. Is Daniel here, Gonzalez? It's a quiz from last time. On our website for the class, you go to Files, and everyone knows the class lecture notes is what I write on the board in here. Course notes is what I just handed you. If you lose them, you can go get them. Exam info, that'll come later. Homework solutions, you probably know about that. Quiz solutions, so the quiz you just took, I just posted while you were taking the quiz, I put it up there. So you can download this. You can look at it as a PDF. Here's the work. You should have got 3 and -1. I won't even require that you check the answers, but they both do work. Okay? So I put the time limit of 7 minutes on that. I mean, when you think about, for a test, we have 100 minutes, right? And if I'm going to give you about 10 to 15 problems on a test, you need to be able to do the problems in about 7 to 8 minutes per problem to get through the test. So again, working on speed. Question? Huh? Oh, no, I'm looking at my work. Okay. So now, because there were 2 radicals, you could have decided to isolate the other one, rather than this one, you could have tried to isolate that one, which it still would have worked. But okay, this is for you to go look at and figure out. I'll have your quizzes back to you next time, and we're just going to kind of keep this format where when I have things to hand back, I'll just lay them out over there, and then you come get it. I don't think I wrote the grade on your quiz, right? That I hand back to you. So it's out of 100. So if it says -20, then you have an 80. But all your grades are online, right? So if you want to keep track of your grades, go to grades. I'm not going to click on it because it can bring up everyone's grades. But click on that. It should bring up your grades. All right. Let's get down to business. Questions on homework? $29. So were you able to look at the solutions online for that one? Let's take a look at the solutions online. So you have 2 radicals. You have a number on the other side. First step is to isolate the radical. So I chose to isolate this one. And then at this point, I have to square both sides. When I square the left side, the radical goes away. When you square the right side, you have to FOIL that out. Now notice I didn't show that work. But that means you have to take the root of x minus 1 plus 2 in parentheses times the same thing, and then do the FOIL. I did do that in class last time. If you do that and combine those together, you get to here. Now, is that the part that we need to talk about, or do you think that's the issue? Okay, so let me show that a little bit more detail. This step right here. You're doing root x minus 1 plus 2, root x minus 1 plus 2. And so when I FOIL this, the first thing I do is I multiply the first 2 together. So when you do the root times the root, it's the same exact radicand. So what happens? You just get what's underneath, x minus 1. Now when I do, let me do it in red. Root x minus 1 times positive 2, I just get positive 2 root x minus 1. Then when I do the middle ones, the inner ones like this, the 2 times this, hold on a second. Yeah, okay, that's good. What do I get there? Same thing, right? Plus 2 root x minus 1. And then when I do the last multiplication, which would be the 2 times the positive 2, I would get 4. Is that okay? Yes? Now, I'm going to combine like terms. So I have an x. I don't have any other x's, right? This x, I can't do anything. There's nothing else that's just x here. I have a -1 and a +4. -1 plus 4. Oh, I'm sorry. Sorry about that. Forgot to turn my ringer off. What is that, 3, you said? And then when you have 2 radicals, right, 2 root x minus 1, add another 2, you should have a total of 4 of them. So you get plus 4 of those radicals. And that is exactly this line right here. Okay? Now at this point, you're in step 3 of the process, which is to repeat the process if needed. And so I'm going to isolate this radical again. So I move the x to the other side, so I subtract x on both sides, I get a 2x. I subtract 3 on both sides, which gives me a negative 2. And I did not divide everything by 2 here. I did that in class. You remember me doing that? I said each one of these has a 2, 2, and then you could do a 2 into the 4. I didn't even do that on the homework. I just squared both sides right here. So squaring this means FOILing it out, which gives you these 3 terms. Squaring the radical means you square the 4, get 16, you square the square root, you get x minus 1. We still good, or yes? Distribute 16 through. Now it's a quadratic equation. So if you have a quadratic equation, you move everything to one side, which is here, and then go about trying to factor that. Does that answer the question on 29, or do I still need to clear something up? What else on the homework? Anything? 65. Oh, okay. Here to here? All right, so let's just talk about that. Do you believe that that's true? That's correct. It's only because the top is 1. So if you look at a fraction, if I take 1 over, let's say, p, and I square it, that's the same as doing the 1 on top squared over the p on the bottom squared. So when you have a power on a fraction, the power can go to the top and bottom separately. And then if I do that, 1 squared is what? 1, and then the bottom p squared is just p squared. So what I've done in this problem, I went from here to here, is equivalent from me going from here back up to here. I'm just going backwards. I'm realizing that 1 over p squared is 1 squared over p squared, which is 1 over p squared. If it was not a 1, you couldn't do it. Good question. That comes up a lot. It's going to come up a lot in calculus, that little thing right there. Does that clarify it then? We good? Okay. Anything else? +51. So replacing the s plus 1 with u. Now, you can expand s plus 1 out. Do s plus 1 times s plus 1 and FOIL. And then you do distribute the, what is that, -5 through, and you get this big quadratic, and then you just clean it up, and you get the same 2 answers. It's just, this is using the substitution to do it a different way. Did you expand it out? Yeah, that's fine to do, but you know, it only works for something like this. It doesn't work for like the one we did that you asked before this. Yes? Is it? Anytime you square both sides of an equation, you should always check your answers or raise it to an even power. You should always check your answers in. And I mean, there's a fundamental reason why, and let me try and explain it without getting us way too off topic here. Whoa. So let me just come in here, and I'm going to tell you right now that I've got this number in my pocket, okay? I've got it written down on a piece of paper, and let's call it x, and I'm going to tell you right now it's -2, okay? So only I know that, right? And then I tell you that this information right here, okay, that's all I tell you, is that x squared is 4, right? Then can you tell me what x is? It's one of two things, right? It's either 2 or negative 2. So that's what you can tell me. It's either 2 or negative 2. And so I pull out see, it's negative 2. So you have to check your answers against the original equation in order to understand what's happening because of the squaring. The squaring always introduces that positive negative possibility. Cubing it won't matter. So if I told you right now that x cubed was negative 8, there's only one thing it could be, negative 2. See, so the cubing or 5th power or 7th power, you don't have to deal with that positive negative issue. So I hope that somewhat clarifies it.
Square both sides, or if you raise an exponent,
even number. Yep. Yes, you should always check.
Or if the answers raised.
No, if you come in and you square both sides, you need to check your answers. And I mean, that's just the general rule of thumb for now. I mean, I think you should always check your answers, especially like if you have that problem that it was 1 over, what was it, x minus 1 squared? Was that our substitution? Was that the one just a second ago? All right, what if your answer was 1? What if at the end of everything you got 1 as an answer? You can't plug 1 in here, you see? Because it's division by 0. So, you know, I don't want to go through like everything you would actually do every time. I just try and check your answers all the time, get into the habit of doing it. It's a way of knowing if you got it right, right? $43. Yeah, we didn't talk a whole lot about this, did we? Okay, so this is it, the substitutions here. I'm going to assume you got all the way down to this right here. And at this point, you take the square root of both sides. When you take the square root on both sides, you do plus or minus. The square root of 1 is 1, so you have plus or minus 1 here. The square root of a negative number is not possible in the real number system. But in the imaginary numbers, it's possible if you're allowed to use imaginary numbers. Now, I told you it's the first time I'm teaching this class, and I've been told to like really talk about imaginary numbers, but I fundamentally have a problem with that. I do not believe this is the class to talk about imaginary numbers. So I'm not going to be real heavy on this, imaginary numbers. What you should know is that, you know, take away from all of this, is that if you ever get the square root of a negative number, okay, if you get something like x is equal to plus or minus the square root of negative 4. If that's an answer you get at the end of something, the negative under the root is going to go away, and you're going to replace it with an I on the outside of the root. So this is going to become plus or minus an I out here, square root of 4. Now, do you know what the square root of 4 is? 2. So this is just going to become plus or minus I times 2, which we write 2I. Now, if you had something like this instead, negative 7, you do the same thing. Take the I on the outside, but the root of 7 is not a perfect square, so you just leave it as root of 7, and that's the way you'd write your answer. I don't want to eat up, we've already almost eaten up like 40 minutes of class, but let me just explain real quickly why I'm not real big on I. You get through Cal 1, well, get through pre-Cal, Cal 1, Cal 2, Cal 3, linear algebra, differential equations, and then at that point you have an opportunity to take a course called complex variables, which is where you actually get into dealing with the imaginary number system. So it is a concept that is beyond the level of a college algebra student. It's too much right now. And I don't even think it's fair to even open the door to that, you know, open the window and even say, hey, look, imaginary numbers, but we're really not going to explain what they are. You take a bunch of other classes and then you know, you get to mess with them. So it's my opinion, let's just stay away from them for now. Square root of a negative number, you get an I out, what does it mean? Don't worry about that right now. Was that a question? No? Okay. How the eyes, like if you plug it in to check it? Oh, they disappeared. Oh, oh yeah, yeah. Okay, so this is, yeah, because the property of I is that when you square I, you get -1. So right here, when I square I, it's -1. And when you take I and raise it to the 4th power, that's, see, it's almost impossible to stay away from this. I hate talking about imaginary numbers in this class. I is the square root of -1. That's the definition of I. I squared then becomes that squared, which should give you what's underneath, -1. So if you take I to the 4th power, that's I squared times I squared. But what's I squared? -1 times I squared again. -1 times -1 is 1. So that's why that I to the 4th went away, really. It turned into 1, and it's not even written up there. Don't worry about it.
So we just box our, if it comes out to one of these items.
Yeah, don't even check it. Just go with that. That's fine. Yeah.
So
that's fine.
That will be a solution.
This is it. There are 2 solutions there. Yes.
Is that how you want us to write it?
Just write it like this.
If it's negative underneath, we just bring the negative.
Just an I on the outside, the negative under the root goes away. It's an unfortunate thing. I mean, it's just the way it is. The reason, shut up, Robert. I need to get to work here. Yeah. Everything I did, like in grad school, was focused on the imaginary number system. And it's not, everyone gives it a bad rap. They think it's imaginary, like, oh, just making up math and stuff. But it turns out that it's a very useful tool. So it's kind of like, God, I can't shut up about it. I'm sorry. I can't do it. It's impossible. Okay, so imagine this. The real number system, right? The real number system, right? Okay. If all you know is the real number system, you are that fish in this fish bowl, okay? What you don't realize is that there's a table out here, and there's, this entire universe of things outside of that fish bowl. The real number system actually belongs to a larger number system called the complex numbers. And so if all you can see is through the real number goggles, then when you get to some difficult engineering problems, it's very challenging to do these problems with just your real number system goggles. But if you can kind of take off that restriction and allow yourself to go out into the bigger number system of the complex numbers, you can make very difficult problems trivial. And so when they first were discovered, the imaginary numbers, they were kind of called imaginary because a lot of mathematicians did not really buy into it at first. And then it was finally shown that they had real value. And so to visualize the number system, to actually see what's going on there, requires a student to understand 4-dimensional space. And that's the challenge. That's why you have to wait till after calculus, because everything in calculus is done in 2-dimensional space or 3-dimensional space, but you stay away from 4. And so once you've got through all the calculus, then you're mature enough mentally, mathematically you're mature enough to start to understand, okay, you've got a function that lives in 2-dimensional, there's something that lives in 2-dimensional space that's going to be mapped over to something in 2-dimensional space. So there's 4 dimensions required to understand what's happening. And that's difficult for people because we live in 3D. That's very simple, right? There's like 3 dimensions to this space, 4th dimension of time maybe. So, okay, it's just more advanced than what we want to do here, right? So I don't like taking the fish and throwing them out of the bowl onto the table and just saying, where the hell am I? And then putting them back in. And that's basically what we do when we start talking about them here. All right. Let's start today's material, okay? No more questions on the homework. So you have all this in front of you. This first part, we could spend an entire 3 weeks on talking about functions and just what they are. All you need to understand is that in this class, when we talk about a function, we have a bunch of numbers sitting in a bowl, the domain. We have a bunch of numbers that are, well, all these numbers are going to go through some machine, which we call a function. That function changes the number into a new number, and we drop that off into another bowl, okay? The bowl that we drop them into is called the range. But that bowl that we drop them into may be part of a bigger space, a bigger bowl, which is the set that it's going into. Let me try and explain that. Let's say that I have in this bowl all the numbers, every number, okay? And the function I have is x squared. Now, if I use the x squared function, when I take those numbers through and I square them, I will drop them off into a set. Let's let this set be all the numbers again. Is every number over here going to get dropped off to every number here? Like, is there a number over there that's going to get taken over to 4 over here? What number over there gets taken to 4 here? 2, right? What gets taken to 9? Over here there's 9, right? Does it come from somewhere? 3, right? And negative 3 goes there too, right? How about negative 4? But if I square negative 2, so yes, but we're not allowed to use imaginary numbers. See, that's why I hate talking about them. We're not allowed to use them right now. Okay, so negative 4 doesn't have anything that comes to it, right? So the set, when we say the set y, see, that's like you could have negative 4 sitting over here. The range are just the things that come out of the function. So if we were using the x squared function, the range would be what? Just positive numbers, right? And 0, because you could square 0 and get 0. So I just want you to understand the difference between the set that you're going into and the range of the function. They're two different things. All right.
So there could be other answers, but they're not in the range of your function.
You could have a set of numbers, right? You could have a set of numbers that your function is going into, but in that set of numbers, your function actually does not go to every number in that set. So this could be all your negative numbers are out here, all your positive numbers are in here, if this is the squaring function. Is it okay to have two numbers go to the same value? So like we had in the squaring one, it went to 2 went to 4 and negative 2 went to 4. Is that okay? Yes, a function is still okay if that's the case. The only thing you cannot have happen with a function is to have one input and two outputs, two different outputs. So I can't plug 2 in and get 4 and 8 or something. You know, can't go to two places. I like to make the analogy of like a car wash, right? You take a car into a car wash. The car wash is the function that cleans the car. Yeah, you get clean car out the other side. You don't put a car in and get 2 cars out. That would be a very nice machine that would do that, right? But that wouldn't be a function, right? So that's functions break down if they try and send something to 2 different places. If they go to the same place, that's okay. All right, domain. The domain are just the things that you can plug into the function. Go back to the car wash. Can you plug any car into a car wash? 18-wheeler? Big old big rig? Not usually, right? I mean, you go to your neighborhood car wash. There's limits on what you can plug into that function. And so with functions in this class, there are limits also to what we can plug in, right? If our function is the square root function, square root, can we take the square root of anything? Well, we can't take the square roots of negatives unless we allow it to be I and forget that. So I, look, just throw I out the window. I's not here anymore, right? So we can't take a square root of negative a number. So there are certain functions that their domain is not everything. So when we say domain, we're saying the things that can get plugged in. The value of the function is when I take a specific car and plug it in, what comes out is the value, all right, the clean car. So for every number over here in this pot, there is somewhere it goes to. That's the value of the function over there. The range, we said, is everything that comes out. I said the range can be all of y or it could be a subset of it. So your range could wind up being everything over there, if the function is appropriate, or it could just be some little smaller group of set of that. Here's where the things that you need for your homework and your test come into play. Determining if y is a function of x. So if somebody gives you an equation, right, so you have an equal sign in there, and you have two variables in it, x and y, then to say that y is a function of x means that you can solve for y, you solve it for y, solve the equation for y, and then you have to check, if you plug in something for x, do you get just one answer out for y? So you're checking to make sure that car wash doesn't go and send out two cars. If that's true, then you can say y is a function of x. You will call x the independent variable and y is the dependent one. So the way we look at it is domain is independent, range is dependent. Go back to the squaring function, right? What can I plug in to the squaring function? Whatever I want, right? It's independent. It can be itself, right? Free to be a number, whatever it wants. What's over here, the range, the 4, depends on that, right? What comes out depends on what's over there. So if I'm 4 over here, that depended on 2 being plugged in or negative 2. So the y's, the coming out stuff, is dependent upon the x. Hope that makes sense. In this case, we will use the notation y is equal to f of x. Y'all seen that before? Y is equal to f of x. And then just be careful you understand that the name of this function is f. We use f because it's a function, right? But you could call it g of x or h of x, or it could be anything. The thing in front of that parentheses with the x is the name of the function. So the name of the function is not f of x. The name of the function is f. Now, you could do it the other way around, and you will do this if you have to take calculus. You will do this, especially in Cal 2. Cal 2, who takes Cal 2 in here? Anyone? Okay, so in Cal 2, sometimes it's easier to work with it if instead of y being a function of x, you can look at x being a function of y. So it's just a reverse process. All you do is you solve the equation for x instead, then you plug in values of y. As long as that splits out or doesn't split out into two places, then we can say x is a function of y. Your y is independent, your x is dependent. You write it this way instead, x is a function of y. Okay, we aren't going to do any of this. You're not going to be tested on that, but I wanted you to at least see it because it happens later. So let's look at these 4 examples, and let's see if these are functions of x. That's all we care about. Is y a function of x? So let's start with A. So the first thing you have to do is solve it for y. Done, right? Done. Next thing, just plug in some values of x and tell me whether or not it gives you 2 answers. So let's plug in 0. What happens if I plug in 0? Okay, what if I plug in 1? I get 2, right? I'm not getting like 2 different answers when I plug something in, right? It's almost so obvious it's confusing sometimes because there's not 2 things happening. It's just one answer. So I'm going to put a check mark. Yes, this is a function of x. Part B, how about this? If you plug a value of x in, is it going to spit just one answer out? Plug in 0, what do you get? Square root of 1. Plug in 3, what do you get? Square root of 4, 2. Plug in 8, what do you get? Square root of 9. So every time you're plugging a number in, you're getting one answer out, right? What about if I plug in negative 2? I can't, right? But that doesn't break the function down. That just means, hey, look, the 18-wheeler is not allowed in this function, right? That doesn't mean it's not a function anymore. It's just that, you know, if as long as the cars coming into the car wash are fit into the car wash, there is one car coming out the other side, if that makes sense. So this is also a function. How about C? So C, we have an equation, right? We're supposed to solve it for y. It's almost solved for y. What would we need to do to solve for y? We need to get rid of the squared. Square root, right? To undo the squaring, we take square root. And that's going to cause a problem because when we take the square root, when we initiate the square root, we talked about this, we have to do plus or minus, right? And so here's where we are. Y is equal to plus or minus square root of x plus 3. Now, y is solved for. If I give you a value of x, is it going to spit out one answer? No. If I plug in 1, I get what? 4. Square root of 4 is 2. So it's saying that y has to be plus 2 or minus 2, right? That's two different answers. This is not a function of x. So this fails. Let's do a clicker check here. Are we good with this or not? You could just say, not a function of x. Pardon? It's pretty much guaranteed you're going to be, if you've got a y squared in there, you're going to at some point need to take a square root, and so you're going to wind up with a plus or minus. Yeah, it's kind of a dead giveaway. Yes. Pardon me? Yes, this does not work. So it is not a function of x. Wait, or which one are we talking about now? Nope, you can't make it a function of x. The only way to get around it is you could break it into two different functions. But we aren't going to do that. How about D? I'm going to write it this way instead. That's the same equation, right? You need to solve for y, so I need to take what root on both sides? Fourth root. And when you come in and you take a fourth root, do you do plus or minus? Yes. You do plus or minus whenever you do an even root, right? Square root, 2. Fourth root, sixth root, eighth root. For all even roots, you always do plus or minus. For odd, you do not need it. Okay? So would this one be a function of x, yes or no? No. So same result here, not a function of x. All right, so you have some of those on your homework. Those are pretty clean, I think. If it looks like it's like almost too obvious, like you plug in x, you're just getting one value out, I mean, that's what's happening, it's a function. Like, don't try and make it harder than it is. Okay, so now, moving on to the next topic, evaluation of functions. So if somebody gives you a function, like I said, the squaring function, we square something, I can define a function in a lot of ways. So if someone gives you a function, how do you evaluate it? So how do you plug things into it? So what we're going to do is by example, we're going to go through this one. I'm going to give you an example of a function, which is that a function? If I plug in values of x here, is it going to spit out one answer? Yes. Also, the fact that I wrote f of x tells you this is a function. You don't have to check it. All right? So what we want to do is in this function, we want to very carefully plug in first -2. That's what this means. Figure out what happens to -2. Then I'd like to plug in negative x. Then I'd like to say what's negative f of x. Then I'd like to plug in negative 3x. Then I'd like to plug in x plus 1. And then the very important for calculus, plugging in the x plus h. All right? And you'll see why that's important later. All right, so let's do this one. Let's start with f of -2. So when we say f of -2, that means we're going to take our original function, which I didn't write down up here. What was it? -2x squared plus 3x minus 8. Okay? So I'm going to take this function. I'm going to replace every x I see with -2. So what do I do here? -2 squared. How do I do a -2 squared here? Like, how do I do this? I need to have that -2 in parentheses because I am squaring whatever I'm plugging in. So if I plug in a negative number, I'm going to square it, right? Square the negative. Now, should I do negative 2 times negative 2 first and get 4? Why not? Order of operations says you do exponents before multiplication. This is an exponent. I have to do this exponent before I can multiply these two numbers together. So what is negative 2 squared? 4, positive 4. I'll get to that in a minute. Plus, let me rewrite the rest of this. 3 times negative 2 minus 8. So that's plugging negative 2 into everything. So I'll have negative 2 times, what did you say this was? 4, so I'm going to write dot 4. And then I'll just go ahead and do this. What's 3 times negative 2? Negative 6, so I'll just put minus 6 instead of plus a negative, then minus 8. So now the multiplication can occur. Negative 2 times 4 is negative 8. And then minus 6, and then minus 8, what's this? Negative 22. So for this particular function, if you plug negative 2 into it, it spits out negative 22. And you should be able to plug any number into this function, right? So let's go to the next one. What if you plug in negative x? So just rewrite this thing. It's negative 2. What are you plugging in? Negative x in parentheses squared plus 3 times, you're plugging in negative x, and then minus the 8. So replacing all your x's with negative x's, see what happens. What happens when you take negative x and square it? What do you get? Positive x squared, which is just x squared, right? But you'll still have a negative 2 in front of it. So it becomes negative 2x squared. And then what about the 3 times negative x? Because this is multiplication, not subtraction. Minus 3x, and then minus 8. And that's it, right? Like, I don't know what x is, so I can't give you a numerical answer. So my answer is actually an expression, right? An algebraic expression here. And this step right here, what this meant was take negative x times negative x, right? Which is the same as negative 1 times x times negative 1 times x, which is equal to negative 1 times x times negative 1 times x, which is equal to negative 1 times negative 1 times x, which is equal to 1 times x squared, which is x squared. I mean, that's like overkill detail there, but that's really what's happening, right? Understand? Everyone got that? The negative goes away because you're squaring it. Yep. But you still have the x times x. So look at this. If you plug negative x in, do you get the same thing as the original function? Are these the same thing? No, they're not. They don't happen to be. Close though, right? There are certain functions that when you plug in negative x, it's the same as what you get when you plug in x. Like they turn out to be the exact same expressions. So if you could have factored the answers, no, I wouldn't have factored it. Just leave it. Yeah. Yeah. Nope, you don't need a factor. Yeah, in fact, that's something that if on a test you got, you were asked to plug in negative x and you got to this and all of a sudden you started to, you set this equal to 0 and then you start doing your quadratic formula, I'd be like, what the hell? What are you doing? Like there's no you're doing way more than you need to, right? So you kind of got to know what you're doing, when to stop. I showed one of my colleagues, I had a quiz in my Cal 2 class yesterday, and I asked for the student to do a certain thing, and they did something completely different. And that's what would happen here if you did that, set that to 0. Now, factoring it and leaving it would be fine if it factored. Just don't set it to 0. Start solving and stuff. Yeah. It's not, I didn't start out as that. What's that? You would lose points if you continued this and created an equation out of it and started solving it. Yeah. Yeah, and time, yes. Okay, let's look at the next one. I'm supposed to plug in, or no, not plug in. Look at this one. It says negative f of x. Negative f of x. All that means, really, negative f of x means negative 1 times f of x, right? So change the signs of the original function. That's all. What was negative, make positive. What was positive, make negative. If you want, you could even show this much detail. It was negative 2x squared plus 3x minus 8. That's what it was. So there's your function. I'm putting a negative in front, so I'm distributing it through to each term. And so it just changes the signs. It becomes 2x squared minus 3x plus 8. Box it up. Don't go setting it equal to 0. And be done and move on. Quick poll, are we okay up to this here? All right, the next, negative 3x. Let's plug in negative 3x. 2, we're plugging in negative 3x, we're squaring it, plus 3, wait, I forgot my negative up front. Negative 3x minus 8. So here are the things I'm plugging in, right? Those are my x's, they're being replaced with this right here. Order of operations says you must square this first. What's negative 3x squared? 9x squared, right? Negative 3 times negative 3 is positive 9. So we have negative 2 out front times 9x squared. And then what's the next one going to be? Minus 9x and then minus 8. Anything else that we can do? Negative 2 and 9? Negative 18. And then this one you set equal to 0 and... No, I'm kidding. You just leave it alone. Don't touch it. There we go. You know, I would say this one you set equal to 0, and then you ask me, well, how do I know? And I tell you, well, you don't know. You just guess, right? That's kind of what English was like to me. Like language, when I took language, it's like, this is the rule, but it's not always the rule. Okay? Well, when is it different? Well, you know what I'm saying? I before E, except after, but not when. No. Can't stand that. Sorry. Okay, next one. Let's do a quick poll here. Uh-oh. These pages got out of order. Where's all my stuff? I'll order them later. I need to just get the fishbowl out of here. There it is. Okay. Quick poll. How many of you are pretty comfortable with everything I've done as far as plugging things into functions so far? We're pretty much okay. All right, here's where things start getting a little bit weird, all right? Let's try F. I need, oh, they went away. I was like, who's the 5%? We got to figure out who that is so I can help them out. All right, I'm now plugging in a binomial, 2 terms. Everything up to this point has been a single term, hasn't it? X, or we plugged in negative x, or negative 3x. When you plug in something like x plus 1, things going to get a little more complicated. Negative 2, we're replacing x with x plus 1, and we're squaring that. Then we're saying plus 3, and then we're replacing x with x plus 1, so I need it in parentheses so that that 3 can distribute through to both the x and the 1. And then I come in here and subtract my 8. Right? I'm evaluating a function at this weird-looking thing, x plus 1. So let's start off with exponents first. You must do this. Right? You must square that, which means maybe you need to go over here and do this thing like this, right? X squared plus 2x plus 1 is what you would get if you put that all together. Not going to show that work. I will write it in blue so that you know where it came from. Okay, so this blue piece right here is what this was, right? Right there. Notice I put it all in parentheses, right? Because that -2 must multiply times whatever that is. And if it turned out to be 3 things, the -2 must hit every one of those things. What's next? Distribute the 3. So the 3 passes through, it becomes 3x plus 3. I still have -8. Now distribute the -2 through the blue parentheses. -2x squared minus 4x minus 2 plus 3x plus 3. Yes, I could have put the 3 and 8 together, but I'm going to wait. I'm going to do it all right now. At this point, collect all your like terms together. So minus x squared, or minus 2x squared, minus x minus 7. So you're putting the -4x together with the 3x, right? And that's your -x. And then you're putting your -2 together with your 3 and your -8, and that gives you what? -7. Factor it. Set it equal to 0? No. Right. Okay. All right, let's redo our poll here. All right, so then, yes. If your answer looks like a function, you just leave it like that. See, what we're doing, it's hard to see the forest through the trees. I hate that analogy, but you know what I'm saying? It's hard to see the forest through the trees here. We are going to want to plug functions, or plug things that are not nice into functions in Calculus 1. We are going to want to do that a lot. And because of that, we have to be very comfortable in this class with the algebra of plugging something ugly into a function. Because you could look at x plus 1 as a function, right? X plus 1 by itself is a function. And what we're doing is we're taking that function x plus 1, we are plugging it into a different function, right? And that's very useful later. All right, next one and last one and most challenging one, I think, is f of x plus h. So it's -2, then you're replacing x with x plus h, then you're squaring it, then plus your 3, and then the x is replaced with x plus h, then you're -8. This is just like the x plus 1, right? Except we have h instead of 1. So you have to go through, and yes, you will have to figure out what x plus h squared is first. So you go do that over here maybe. Is x squared plus xh. I'll show a little bit of the detail here. That's what you would get if you FOIL, but if you collect like terms. Melina? How did you know that was x squared plus 2xh plus h squared? You've done this enough? Are you doing it mentally? You've done it enough? It becomes almost at some point just second nature, okay? If you've done it enough. Or if you see it all mentally. Some people just see it, very visual. All right, so we have -2 x squared plus 2xh plus h squared. That's what I got when I put that there, right? Is this correct? Oh yeah, I have to have parentheses, right? If I don't put the parentheses, then I'm not going to distribute the -2. Everything's going to be off. What should I do over with everything else there? Distribute 3 through the x and the h. So plus 3x plus 3h. And then minus our 8. Anything else to do? Distribute the -2 through. And then I'll look at what I've got there. So negative 2x squared, what now? Minus 4xh minus 2h squared plus 3x plus 3h minus 8. And now I collect any like terms together. There aren't any like terms. Well, hold on. X, they have to have the same exact variable, same variables to the same powers. So I have an x squared here. I don't have anything else with x squared. I have xh together. I don't have anything that has xh together. I have just h squared. Cannot put that together with h, right? They'd have to be both h squareds. X, just x by itself. Don't have any x's by itself. H by itself, nothing. Numbers by themselves. This is it. This is what we get. That's what you get for plugging that in. Oh. All right. Gosh, it's almost fun. Yes? Yeah, let's see. Did you all do okay with that one or not? Get used to this because it's going to keep coming. And the functions, this f of x plus h is going to keep happening, and the functions are going to get more and more complicated. So it's going to be harder and harder and harder to plug in the x plus h and clean it up. That's what we're going to work on getting good at. All right, so we did this one where we plugged in, we evaluated, we kind of get the idea of what it means to evaluate functions at different things. When you're looking at a function, y equals f of x, and you are asked to evaluate it at some value like we did here, then the thing you're plugging into the, that was supposed to say into, the function, the thing which replaces the x, is called the argument of the function. So what's the argument of this function right here? Argument here, x, here, negative 3x, here, x plus 1, here, x plus h. That's the argument of the function. It's the thing that's going and getting plugged in. Just some language, okay? Argument. Right here? I wish my program, I use Mathematica to do my notes, and it doesn't have a spell check. And I don't check my own spelling. So thank you. I appreciate that. All right. Finding domains of functions algebraically. All right. So we were talking about the domain of a function, right? We were talking about how certain things can get plugged in. Some functions can't handle 18-wheelers and things like that. Well, what we want to be able to do now is I give you a function. Just here it is. F of x is this. And you tell me what can be plugged into it or what cannot be plugged into it. And in a college algebra class, the only issues that we run into are what? Division by 0, okay? We always are going to ask ourselves, when I look at this function, do I ever get division by 0? Because the function can't do division by 0. No function can do that. So if I ever want to know if the function has division by 0, I look in the function, I look to see if there are any fractions, and if I see a fraction, I ask myself, is the denominator ever 0? If that is, then I need to throw those out of the domain. Those are not allowed in. Now, the other problem we can have here in a college algebra class is square roots of negative numbers. Can't have that because we can't have imaginary numbers. And not only square roots, but any even root. But we mainly will deal with square roots. So that's the main two things that we're going to look at when we talk about domains of functions. Do we have division by 0? Do we have negatives under square roots? Important, this is real important, when you're looking for domains of functions, always check for domain issues prior to algebraic simplification. Prior to algebraic simplification. And I will actually elaborate more on that when we get to example E. You'll see what I mean by that. All right? So let's work through these. Y'all doing all right? The week is almost over. There they are. Everyone, can you read that on the page I have? Yes? Okay, let's do, find the domain for part A. So for A, I give you a function f of x equals square root of x minus 1 over x plus 4. All right, so two things we're looking for, division by 0 and negative numbers under roots. So could you ever get division by 0 here? If I make the denominator 0, then this function is going to freak out, isn't it? Okay, x cannot be not 4, negative 4. So maybe you're just looking and seeing that, right? But let's try and get an actual algebra technique for doing it. We look at the denominator, which is in this case x plus 4, and we figure out where it is equal to 0, all right? Whatever answer we get, we throw it out, right? It's not allowed in our domain. So this, what type of equation is this that I'm solving? It's linear. I know how to solve linear equations. I just move things over, I isolate the x, right? So I get x is negative 4. What does that tell me? For the domain, x should not ever be equal to negative 4. Do you know what these three dots are? It's the first time I've used them in this class. Y'all ever seen that before? We use this in mathematics to represent the word therefore. All right? So you'll see me using this throughout class. It's just shorthand. So I'm saying what I did was I set the denominator equal to 0, I solved, therefore the domain cannot have that number in it, right? Because if I plug negative 4 in here, I get 0, which gives me 0 here. That seems trivial, I think, with this problem, but what if the denominator there was quadratic, right? Like a quadratic expression, you would do the same thing. You'd set the quadratic equal to 0, then you'd go through and solve that. Is that the only problem we have in here? Is that the only issue we have to worry about? Can't have a negative under a root. So look up here, right? What can you tell me about that? That thing in blue there. This was the yellow part of the problem. The blue part I'll do over here. What can you tell me about the thing underneath this root? It cannot be negative. What's another way of saying something can't be negative? If it can't be negative, it has to be positive. Could it be 0? You can take the square root of 0, right? Square root of 0 is 0. So what I'm going to write here is that the x minus 1 must be greater than or equal to 0. What I need is the thing under the root, which we call the radicand. I need that to make sure it's not negative. So I'm going to figure out when it's positive or bigger than 0. Anybody know what type of thing this is called? An inequality, right? This is an equation. This is an inequality. This was a linear equation. This is a linear inequality. The way you solve a linear inequality is the same way you solve a linear equation, with one exception. If you ever divide or multiply both sides of a linear inequality by a negative number, what do you have to do to the inequality? Flip it over. That's the only difference. All right? I'm not going to do it. I'm just going to add 1 to both sides of this. And what is it going to tell me? X must be bigger than or equal to 1. Now let me put these pieces of information together. And to do this, I'm going to draw a number line to help everyone and myself see what's happening. I suggest you draw a number line also. All right, so here's our standard number line. Remember, our function is taking numbers, plugging them in, spitting them out, right? I'm trying to describe to you what you can and cannot plug in. Right now, I know from the red part, x cannot be what? Negative 4, right? So negative 4 is somewhere over here. I'm just going to mark it negative 4. I'm not even going to like count out. I just know it's to the left of 0. And I know I cannot have that number in there, right? So I'm going to put this open circle here to let you know I don't want that number, right? But then what does this tell us right here? X must be greater than or equal to 1. Where's 1 on the number line? Somewhere around here, right? Greater than or equal to 1 would mean, I'm saying everything out there, right? To the right of 1, forever, never stop, right? So I'm like shading this line this way. Everything out there would work. How about 1 itself? Yes, I'm allowed to have it 1 because it says greater than or equal to 1. So you can do one of two things here. You can put a solid dot there, or you could also put a bracket there. Sometimes books use brackets. Either way, you need some way of knowing you do want that number in there. And then what you do is you look at this and you try and describe to me the answers. Well, and it has to satisfy both at the same time. So we know -4 won't work, right? How about 0? Will 0 work? It works for that one, right, for the one in red, but it does not work for the one in blue. So if you look at both of these together, the only thing that works is everything bigger than or equal to 1. Do you all follow that? So how do I write that? X is greater than or equal to 1, right? Now, there are two ways that we write domains. There's set notation and there's interval notation. You need to be able to do both. Set notation goes like this. X such that, we've seen this before? All the x's such that x is bigger than or equal to 1. That's set notation. What does this line right here mean? Such that. This is set notation. The other notation that you need to be able to use called interval notation actually just works off of this right here. How do you say from 1 on forever? You say 1 comma to infinity. And then you put a bracket to the left of 1 and a parenthesis on the infinity. So this means everything from 1 on, the bracket tells you include 1. If I did not want to include 1, what would I put instead of a bracket? Parenthesis. What about infinity? Why don't I use a bracket? It's going forever, and therefore it's not a specific number you stop at. So you can never have a bracket on infinity, ever, ever. Interval notation. So this is set notation. And this one is interval. You'll see when you look at my solutions for your homework that I might even put in here in the front, like X, like this. I might write X with this little weird E looking thing. And this means X is an element of this interval. And then I think later on in the homework I stop writing it in the solution. So if you just wrote this in black right here, I'd be happy. But if you ever see it in another book this way, you know, you can't say I never showed you. You need to be able to do both. Yep. On a test, I might ask, give me the answer in set notation. I might say, give me it in interval notation. Just, yep. Well, let's look. Yeah, we're going to run into some other issues here. How about this next one? G of x is x cubed minus x squared. What are the two issues we're concerned about in this class? The two things we're worried about in terms of domain. Division by 0 and roots of negatives. Do you see any fractions here? Do you see any square roots? That means you shouldn't have any problems plugging anything you want into this. Any number. Right? You're never going to get division by 0. You're never going to get a square root. So no problems. That means how do you say you can plug anything you want? Everything, right? So let's do the set notation interval. Here's set notation. The set of all x's such that x is an element of the real number system. Double struck R, This is a capital double struck R. We use that to represent all real numbers. That's one way of doing set notation. I'm going to show you multiple set notations because people come from different places. Another way would just be, say, hey, look, my x has to be between negative infinity, bigger than negative infinity, but less than positive infinity. That's another way you could do it in set notation. I like the double struck R. It's shorter, it's to the point, right? Now let's do interval notation. So where am I starting, where am I ending? Left to right. Negative infinity is where I start, and I end where? Positive infinity, and you always put parentheses on both infinities. There's your interval notation. I like that also. Both of these are set. So this is set up here. This is a set notation, and down here is the, I'll just put int, interval. Yes. Yep. Next one, H. Capital H of x. What's the name of this function? Just H, right? The name of the function is capital H, right? So maybe this is a heat function. It's a function that represents the heat on an object at a certain point in time or something. Who knows? That's why you would want to name a function, because it might actually represent something, right? Cost function, profit function. So H of x, capital H of x is this. Okay, do we have square root? No. Do we have a fraction? Yes. So whenever we have a fraction, we take the denominator, whatever it is, we come over here and we ask ourselves this question. Is the denominator ever equal to what? 0. If it is, it's not going to be good. How do I solve this equation? You want to take the 1 to the other side and make it a negative 1? And then what? Take the fourth root. Fourth root. What's the fourth root of negative 1? And by the way, it's plus or minus, isn't it? Because we did fourth root anytime you do a new. But the fourth root of a negative number is the same thing as the square root of a negative number. It's not possible unless you introduce the imaginary numbers. So there are no issues with this denominator. You can never, if I tell you right now, you can only plug real numbers in, you will never be able to make that 0, ever. Just think about it. You start with 1, right? Then you add to it a number that's going to be what? At least positive. I mean, positive. The smallest it could ever be is what? What's the smallest x to the fourth could ever be? 0, right? So you start with 1, you add nothing. You're still bigger than 0, right? If you take 1 and add any other number to the fourth power, it's going to add a little bit on top of the 1. It's impossible. Do you see algebraically it's not possible? Do you see just thinking through it it's not possible? You should be comfortable both ways there. Just saying, oh, wait, that's not, it can't happen. Okay, so what if that can't happen, then what's the domain? Everything, right? All real numbers. So it's the same answer as the one before. I'll just do the set notation. If you just wrote this, if you just write all real numbers, I'm okay with that. Yeah. Just like that? That's okay with me too. Yeah. Just realize that some instructors, as you go on, want you to be very precise with your notation. All right, let's try and get another one in here. Oh, remember the fishbowl, right? The fishbowl is double struck R. The fishbowl lives in a larger universe, double struck C. Double struck C is your complex number system. And then within the fishbowl, there are smaller sets. Double struck Z are all your integers. And there's like different variations of things, but Just kind of sharing that with people who are doing more math. Um, what's our next one? Oh, nice one. Okay. We have part D, capital T of little t. Capital T of little t equals square root of little t over 9 minus t squared. Okay, now we're getting into like exam type problems. All right, the first were just like warm up problems. These are like more what you're going to see on an exam. All right, so the two issues we look at, division by zero, square roots of negatives. I think we've got both, right? So let's try and figure out. You want to start with the division by zero? Okay, let's look at this. We need to look at the 9 minus t squared. We need to figure out where it's equal to 0. Yes? Yes. Can I factor it here? Yes? Okay. Difference of squares? Is that what you want to do? 3 plus t, 3 minus t? T is 3. You get two answers there, right? Pardon? It's a 9. Sorry, yeah, that kind of looked like a Q, didn't it? It's 9. Yes, that would work. Could you also have moved the t squared over, made it positive t squared, and taken square root on both sides? Yes. Either way, you should get two answers. So what are we going to say? Therefore, for the domain part of this, we want to make sure what? T is not equal to positive or negative 3. All right, we got to make sure that happens. I missed a button. So when you're looking at the denominator to 0, you get the answers and you throw those out. Now the square root part. What can you tell me about the square root part? Can't be a negative. So how do we say can't be a negative? T must be greater than or equal to 0. And there's nothing more I can do with that, right? T greater than or equal to 0 means T's got to be greater than or equal to 0. There's no solving or anything to go. So I think now I'll draw a number line real quick, see if that'll help me out. From the denominator, 3, negative 3, we throw these two out, so I'm putting circles, open circles here. Those cannot be in my answer. But then t being greater than or equal to 0 means everything from 0, which way? To the right. So I do want to include all of this, except I can't include 3. Do I want to include 0? Okay, so do you want me to do the dot or the bracket here? What do you, bracket? Or if you like the dot too, you can do a dot and a bracket, or just the dot, or just the bracket. Doesn't matter. The bracket kind of helps you remember what you're going to use when you get to the interval notation. So how do I say everything from 0, including 0, until I get to 3, but not 3, and then from everything from 3 on? So let's try the set notation first. Set notation is a little bit more challenging here. It's all the numbers x such that x is greater than or equal to 0, and comma, x is not equal to 3. Now, this comma can be used in math for and, but there is technically an and symbol for math. You don't know what it is? This is the or symbol, and this is the and symbol. So you could have replaced this right here with the, it's like they call it the caret. But it can be confused with exponent. So the comma is just as well. You can read this as all the values of x such that x is greater than or equal to 0 and x is less than, or sorry, not equal to 3. Now let's try the interval notation. Yes, it should be t. Thank you, Melina. T. Our variable was t. So how do I do interval? Everything from 0 to 3 though, right? I need to stop at 3. Do I want to include 3? Do I want to include 0? Yes. Okay, that's part of the answer. The other part is everything from 3 on, isn't it? So I write 3 to infinity, never include infinity, so parentheses. Do I include 3? No. It's those two intervals, isn't it? And so anytime you use interval notation, you have two intervals, you throw them together with a union symbol, a big U. Means this set unioned with that set.
The second number is the number that you're not including.
Nope, it's as if you're moving from left to right on the number line. You're starting at 0, including 0, moving to where? To get to 3, but don't include 3. Then start off where? Right next to 3, and then forever. This basically has the effect of jumping over 3.
Okay. If you wanted to include 3, then you would use the bracket, like say.
I would have done a bracket here.
Or on the right side. I mean, on the right of the U. You would put.
If I wanted the 3 there, yes, yes. But if 3 was in there, then I would have never stopped it. I just would have gone from 0 to infinity, right? This goes back to, this idea that there is no number closest to 3. So how do I say stop when you get to 3 but don't include 3? I can't tell you where to stop because you can never actually get there. Yes?
So when there's a 3 and then the union 3 is the same number, it means that it does not include.
That's right. Okay. It's not going to include it. This is telling me, okay, I can stand at 0, right, on 0. I can start walking down the number line until I get to 3. How close to 3? As close as I want. Can I be 3? No. But how close? Does everyone understand that if I give you any two numbers on the number line, any two, there's always one in the middle of them? Yeah. Think about this for a second, because I'm running out of time. We're gonna have to stop right here, but I just want you to look at the numbers between 0 and 1. How many numbers are between 0 and 1? Infinitely many? There's actually not imaginary numbers on this part of the number line. They actually go vertical, but that's different. So everyone agree there's infinitely many numbers here?
Yep.
So like I could take 1/2 and then 1/4 and right, 1/8 and 1/16, and I could keep doing that. How long? Forever, right? So there's infinitely many numbers in here. Yes? I'm going to tell you a quick story. I have 5 minutes, so I get to keep you here for 4 more minutes. 4 minutes. I'll tell you a story. Any of you plan on going to grad school? Okay. I always tell my students this story because graduate school is like a life-changing experience because it's school at a level you really aren't ever really prepared for, and so it usually becomes your life. I mean, that is what you become consumed in. I mean, it can only be your 90% of your life will focus around school. The other part will be sleeping and eating, pretty much. So when I was in graduate school, I had to give up the whole social part of my life. And so what I would do, though, because I didn't want to go crazy, is I would, there's no need to record this.